I want to thank Dr. Naresh for the very generous introduction, and it's opportunity for me to meet with Naresh, of course. I know him for quite some time, and also Dr. Seshagiri Rao, who I've known for a very long time, and also meet members of this organizing committee. And I made some new friends today, Professor Sharat Babu and all the others. Dr. Ramsagar, I've been in touch with them. So thank you so much for this opportunity. I really appreciate you having me to this wonderful campus. So I just wanted to say a bit about this beautiful NIT Warangal Chemical Engineering Department. NIT Warangal Chemical Engineering Department has been important and a significant node for chemical engineering education and research since it started in 1964. And several graduates from NIT Warangal's Chemical Engineering Department have done postgraduate programs at NUS and are very, very successful across several domains. So I just listed out a few people that I've had the opportunity to interact with, the alumni of this department. And the people that I show in blue color, Dr. Pawan Kumar, Madhukar Dudappa, Mrinal Jain, Ram Prasad Elchuru were my own graduate students. And the other people that I've listed there, I've either taught them or I've been in the thesis committees, etc. So your department produces wonderful students, and I hope this continues for a very, very, very long time. So congratulations to the department. Now, getting into my talk, right, I just wanted to provide an overview of the kinds of things that is done in this field. Now, almost everybody is interested in this area. It's become very mainstream, so it was a niche area some time ago, but I think the democratization of this field has happened. So, the ideas that are here is put to use in many domains by many people, and it will also be abused by people, right, because it's easily accessible. There is a great chance for people to just use it indiscriminately without understanding its pitfalls, etc. So we have to approach this field with caution. So I thought for this audience, I'll provide an overview. For some of you, it may be a good introduction to the field. If you're already doing advanced work in this area, you might feel that this is not exactly what you wanted. So I'm just trying to minimize the math, etc., etc. So if I do a course on machine learning or AI, I will do a lot of maths and stuff. Here I just wanted to present some qualitative overview of the field. Okay, so I hope it serves as an introduction to some of you. Now, our field, right, chemical engineering, engineers as people, we like to abstract things, right? We do experiments, we observe our processes, we collect data, and then we like to abstract it. We don't want to just record the data in some spreadsheets and keep looking at it, right? So we always are looking for models. We want to create those abstract representations and then use it for a variety of purposes, such as design, control, optimization, etc., etc. Right? So our main business is to work with symbols and use symbols to kind of condense all our observations into simple representations, right, and use them. So as you very well know, there are a few things that has happened. One is the industry is awash with data. Okay, since the early 1990s, there have been renaissance in this field. That means people just don't keep data archived. They want to actively use data, right? So from the databases, data is frequently brought into the computers, analyzed, and then information is taken out of it, and then actions are taken based on that information, right? So previously data was collected, little data was collected, it was just archived. And when some major accident took place, they will take the data and try to troubleshoot and try to find out the reason. But now with all the improvements in sensors, right, and storage has become cheap, right? Data storage has become cheap and accessible. People are saying, okay, we can store large amounts of data that comes from a lot of sensors in the process. Not only that, we can actively work with the data and draw information from it, and then, as I said, do some actions. All right. So, as chemical engineers know, we try to get representations of the physical world. And we reactors, distillation columns, other kinds of separation units, heat exchangers, all kinds of processes, right? So we like to represent the physical world, and there are broadly two branches. One branch that you see from the left-hand side, that's called conceptual modeling. So it's based on thought experiments, right? You can make assumptions about the mechanisms that are happening in the process, the phenomena that takes place in the process, and then you can invoke the conservation laws, right? All of us know conservation of mass, conservation of energy, conservation of momentum, right? So those conservation laws are there. And then we use other relationships, right, which are called constitutive relationships, which link the variables to each other in the first principles model. So together, the mass energy momentum balances and these constitutive relationships that we get from our experiments on processes, together they are called fundamental models, right? You can call them as first principles models. So that is one route to come from the physical world to the mathematical model. Of course, there are many approximations on the way, right? You cannot model any process in all its glory, right? It's very complex, high dimensional, etc., etc. So if you model it in all its glory, you may not be able to use it for many purposes. It will be there, but you cannot use it. Because we want to use it, and we also want to use it real time, we like to do approximations. And basically, engineer's job is the art of approximation. We approximate so that we do not lose the essence of the process, right? So we take care to approximate or catch the most important things in our model. So that's the route on the left-hand side. And the route on the right-hand side is empirical modeling. That means you do actual physical experiments on the process, and then you collect data, right? So I was listening to two talks in the previous session. The last two talks I was able to listen because I was in this room, and they were based on data collection, right? They had some hypothesis, they had some thing to prove or disprove. So what they went ahead was to collect data by doing experiments on the process, and then the data, what they did is they used regression model. In the olden days, they did simple linear regression, for example, and they kind of came up with approximations of the physical world based only on the data that they collected. So the right-hand side, the regression model, now you have other high-level models, very complex models, right? For example, neural networks are very common these days. Basically, they do regression, right? They do non-linear regression in a very interesting kind of way. But nevertheless, those are models that are based on correlations or patterns in the data. There's nothing fundamental to those models, right? So, for example, in the olden days, the regression models did not enforce mass energy balances. They just said, this is the inputs, this is the output. I can find a mapping function that relates the inputs to the outputs. But that route is a very convenient route. Okay, because you can do the experiments, you can collect data, you can fit a model, and you can make use of the model. It's like driving a car without knowing anything about the combustion engines or transmission. You don't know anything about the mechanics of the car. All you know is, in the car there are brakes, there are accelerator pedals, and then you want to maintain a certain speed and a certain direction. That's your output. And then you know if you press this, if you turn your steering wheel by so much, the car changes its direction by so much, etc. So you basically work on the basis of sensitivities, right? A 1 degree turn in the steering wheel changes the direction by 6 degrees, for example, right? We think in those terms. And a little push to the accelerator will make the car go faster by so much amount, right? So we just do some experiments as you sit in the car, and then you drive your entire life without any accidents or anything like that. But should the car break down, you don't know what to do, right? The only thing we do is make a phone call to the nearest mechanic or something. That person comes in, because that person knows first principles, is able to troubleshoot, etc. So the point is that right-hand side route is very convenient, but you do not know anything about the mechanisms that are underneath it. So that way it is not a good scientific engineering way of doing things, right? But we are able to manipulate, control, optimize processes just by following that route. So this route, using conservation laws, equation of state, etc., takes a very long time to build. It requires a lot of expertise, right? Or you require a lot of fundamental knowledge. So it takes time to build. So that is the negative of the left-hand side, the fundamental model route, but you can say a lot about the process insights. You can maneuver the process even better if you understand the fundamentals, right? So that route has convenience, that route has convenience. Both of the routes have some negativities as well. In any case, you come up with a mathematical model at the end of it, right? So these were the two routes, and of late, you see more emphasis on the database models, the right-hand side, right? The left-hand side, people think it is still a bit difficult to do, to come up with a full model, etc. So the right-hand side is getting even more and more usable by people, right? So that is the stage that is set. So if you look at empirical modeling route, right, there are so many types of methods. I'm sure some of you are familiar with these things. So the linear regression comes first, it's the most simple thing. Then people understood that this linear regression will not work in situations where you had input data that are correlated, right? In the past, you had very few sensors in the process, and those sensors gave independent pieces of information. So it was easy to build a regression model, simple regression model. But later, when you started measuring many things, what happened is the variables were very correlated. So if variables are correlated, matrix inversion becomes impossible. It becomes difficult or it is inaccurate. Therefore, you have to come up with some special methods to kind of overcome this data correlation problem, right? So they came up with methods like partial least squares, canonical variate analysis, and things like that. This is the field of multivariate statistics, right? Linear regression, multiple linear regression is already multivariate. But when you have data that comes in real processes, the data correlations make sure that the linear regression method is not the best. So you got to invent other tools, and they did it beginning 1990s. These methods became very popular in the chemical engineering field. So if you look at basically a lot of activity happened in Canada at that time. John McGregor's group, Professor Siri Shah's group, etc. They kind of did a lot on industrial processes with partial least squares and those kinds of methods. Then there was a natural need to look at non-linear versions of these methods, right? Because many people said data is not just linear, data is non-linear, right? When you have multiple grades of products, right? Multiple grades of polymers, multiple grades of paper, etc. The data tended to be non-linear. So you had to extend those methods by implementing some non-linear versions of partial least squares. Then the things like support vector regression, all those kinds of areas came out. And then people also looked at methods that are non-parametric, right? That means the methods will not give you an equation as an output, right? It's very, very powerful actually. The non-parametric methods, people do not pay attention to it. But when you process your data through the non-parametric methods, you will get graphs instead of equations. And by looking at the graph, you will know what is the kind of non-linearities that are there in the process. Is a single variable non-linearly affecting the output variable, or variables interact and they have a non-linear interaction effect, and that affects the output variable, etc. So these non-parametric methods are very powerful. Some of the methods are called, listed there, alternating conditional expectations, ACE, and MARS, multivariate adaptive regression splines, etc. These are very, very powerful methods. So if you are a student in any field, right, for example, many of you must be chemical engineers here. So whatever area you are working on, whether you are working on materials or biology or whatever field you are working on, these methods are extremely useful for you to get an understanding of what the process is. Once you process your data through non-parametric methods, then what you can do is you can fit parametric models to that. Parametric models is like y is equal to ax1 plus bx2 plus cx3. That's called a parametric model, right? You have parameters, a, b, c are the parameters that help you to link x1 to y, x2 to y, etc. respectively, right? That's a parametric model. We all do that. But these non-parametric methods, I found in industrial practice, it is extremely useful, right? To do some exploratory analysis of data. Then there are other methods like classification and regression trees, decision trees, random forests, and stuff like that. How many of you here are using these methods like HART or random forests?
Many should be using.
Yes. What are you using it for?
biomass, bio biogas is
Okay.
based on the nutrition.
Right. So generally you come up with some rules kind of thing, right? If person is male and salary is less than $10,000 per month, that person might default on credit card payment. This is the kind of rules that people can come across. In chemical processes, you can have a rule like that. If temperature less than 64 degrees and pressure greater than 5 atmospheres, then this, right? So you can kind of create those kinds of rules, and that becomes these decision trees or classification trees, etc. So these kinds of rules you can obtain from analysis of data, okay? And then you can use it for many purposes. Now, when you talk about data, right, you have to worry both about quality and quantity. Sometimes, right, people think if you have data, you can produce some magic out of it, right? They'll say, oh, I gave you 1,000 samples of data, get some insights about the process. That is not a right thing to do, right? Usually there are people in the business side of the industry, right? So they go and promise clients something big. They say our tool can do this or our tool can do that. And then they come and tell the technical team, you better deliver on that, right? So if you have a lot of data, but the data is not of great quality, you're going to get garbage, right? You have heard this adage, right? Garbage in, garbage out. So the quantity of data is not the most important thing. The quality of data is very, very important, right? So that's one thing I want you to keep in mind. So if you do experiments on the process, right, and you have information-rich data, then these methods can help you with lots of insights you can understand about it. But if your data happens to be routine happenstance data, right, that's normal operating data, then you may or may not get benefit from the data. Okay? So the excitation in the inputs is very, very important. Unless I excite you, I will not be able to learn about you. Right? You and I can sit in this room for ages, right, for centuries, and if I don't ask you something or you don't answer or the other way around, we are not going to understand each other, right? So the point is you have to perturb, you have to let the process respond, and then from that input output you can get a lot of information about the process, right? So the quality of data is very, very important. Quantity helps, but not to that extent. And I also want to point out a few things. One is chemical engineering field per se, right? It is not like what is done with Google or other companies like that. Okay? There they have lots of pictures of dogs, cats, things like that. They can classify whether it's a dog or a cat or a squirrel or none of these, right? We do not have that much data. Though I said there is a lot of data, but we are not into this domain of big data. To be honest, chemical engineering is not like that. We are still a domain with limited amount of data, not huge amounts of data that people talk about. So we are having small quantitative data relatively. So the quality of data is very important for us, right? So that's something should be kept in mind while using any of these tools. Now, after you have looked at linear processes and non-linear processes, then the natural question is, many of our data is time series data, correct? Things happen in sequence of time. The world is dynamic, the world is not static. So if you collected only steady state data, the previous methods will do a very good job. But if you have time series data from dynamical systems, and our systems are mostly dynamic, then you need architectures and algorithms that can handle time series data. So we have a lot of time series models like I listed there, right? So those methods have been developed from about, let's say, 70 years ago, and it has reached a very good state. Then the next mix comes into play, right? You have non-linear data, data coming from a non-linear system that is also dynamic, right? So then you have the NARX models or the NAR-MAX models. ARX means autoregressive with exogenous inputs, right? So if you get into time series literature, all these things will be there. But these are simple models, and once you understand the models, and once you understand the quality of data, the tools are available, then we can use it, right? It is a wrong thing to just use the tool because it is just there. So understand what are its assumptions, what are its implications, and then we can use it, right? So that we can benefit from it. So those things were there. Then neural networks, right? I've listed it separately. This is a big thing nowadays, right? People talk about deep learning, right? And many things, right? Convolutional neural networks, recurrent neural networks. You have so many varieties, right? Every day there is something that happens in the field. This neural networks, right, had a very interesting history. So it was discovered by very smart people long back, right? So there's a whole way in which it evolved. But at some point in time, people did not believe that neural networks can deliver, right? There were companies that developed software and sold it to chemical companies, but the promise was not met when they actually implemented processes, those things in the plant. For a variety of reasons. One is people typically overpromise, right? There's a new thing that's out there. You must have heard about this hype cycle, right? So things go through a hype and then it falls and then reaches a plateau somewhere, right? So this hype cycle is there. So if you are on the hype, as it increases, people think it will deliver a lot of things for you. But sadly it doesn't, because people did not pay attention to the quality of data per se. And sometimes these models, neural network models, can overfit. That means it can fit noise, right? So overfitting is a problem with any modeling effort. Particularly with neural networks, it can happen a lot. And when you overfit any data, you are modeling noise into your thing. So the art of modeling is where is the boundary between the signal and the noise? So when you collect sensor data, right, you have signal part of it, you have noise part of it. If sensors get you data without any noise, then there is no problem. It's an easy job. But unfortunately, we have noise. And there are very interesting types of noises in process data. And it changes from industry to industry, right? For example, in mining, metallurgical industry, the noise is very, very high, right? In petrochemicals and oil and gas, it's relatively low. So that is there. So the point is, you should not basically model noise, and then that would be called as overfitting, right? So that is the problem with neural networks. So when I joined Mitsubishi Chemicals in 1997 my boss told me, don't do anything with neural networks. You do anything else. We do not want neural networks because we invested quite a bit and it did not work for us. So we have dismantled all the things that were done with neural networks. Now 20 years later, everybody uses neural networks for modeling processes, etc. And there are some very smart algorithms that are out there now.